Welcome to our competency-based question series designed chapter-wise to enhance your conceptual learning and one. A white light is used to illuminate the two slits in a Young's double slit experiment. It results in the overlapping interface patterns on the screen as each wavelength corresponds to one interference pattern. And a diagram is given to us. At a point P that is directly opposite the slit S1, find the series of wavelengths that will result in minima. So this is the question from Young's double slit experiment. And before solving it, let me just give you a brief introduction that how we can obtain the conditions for the point on the screen, whether it is a maxima or minima based on the path difference. So this is our Young's double slit experiment and it is for monochromatic source. Here X is monochromatic, means it has only one wavelength. Now we can write the distance y on the screen from the central maxima in terms of path difference. So the path difference between the two waves coming from S1 and S2, and when they are reaching point P, it can be written as S2P minus S1P, and this path difference we have obtained as dy upon capital D, where D is the distance between the slits, y is the position on the screen from the central maxima, and D is the distance between the screen and the slits. So this is the value of path difference. Now I can write this path difference and I can find out the value of maxima or minima at point P based on two conditions. So when path difference is n lambda, then we get maxima, and when path difference is n plus half lambda, then we get minima. So this is the condition for maxima and minima. Now I can rearrange it and I can write y is equal to d times the path difference divided by small d. So the distance of the point P from the central maxima, it can be written in terms of path difference, and for minima I can put this path difference as n plus half lambda, and for maxima I can replace this path difference as 1 lambda. Now we can solve the question. So in the question it is given that at point P we are having minima. So what I can write, y is equal to capital D upon small d into path difference. And since this path difference is minima, I can write this path difference as n plus half lambda. So y can be written as capital D upon small d multiplied by n plus half lambda. And from this figure, I can obtain this thing that this y, it is equal to small d by 2, because this total distance is d and this point is the midpoint O. So y has to be half of the distance between the slits. And it is given also that point P, it is directly opposite to the slit S1. So now I can replace this y with small d by 2. So this implies small d by 2 is equal to capital D by small d multiplied by n plus half lambda. And when I reshuffle it, I can write down the value of lambda. So from this, I can find out lambda is equal to small d square upon 2 capital D times n plus half. And the value of n, it varies from 0 plus minus 1 up to infinity. So now when n is equal to 0, lambda will become equal to d square upon 2 times capital D multiplied by half, and that will be equal to d square upon capital D. Similarly, when n is equal to 1, lambda becomes equal to d square upon 2 times capital D, 3 by 2, because 1 plus half is 3 by 2, and then it becomes d square upon 3d. Similarly, for n is equal to 2, we get lambda is equal to d square upon 2 times capital D multiplied by 5 by 2, and lambda becomes equal to d square upon 5d. So in the question, it has asked that find the series of wavelengths that will result in minima. So the answer is the series of wavelength lambda that will result in minima at P will be lambda will be equal to either uh, d square upon capital D, or it may be d square upon 3 capital D, or d square upon 5 times capital D, and so on. So this is the answer for this question. But we need to remember this formula, that the distance y on the screen point P, it can be represented in terms of path difference by this formula. Keep learning, keep practicing, keep excelling.